Это полно народу.
Ну, специально для Эвера. Окей.
Okay,
I will start.
We start. Yes.
So I plan to talk about relationship between two geometries. One is our favorite jet geometry, and the second is less favorite but very popular information geometry. So I will start with I hope soft introduction is this information geometry. It will be not correct, but what they call information geometry is geometry on the manifold, where points are some probability measures. So I will show how to get a situation when you should start some geometrical constructions on manifolds with this condition that points on manifolds are probability measures. Okay, so let's start at the very beginning. We take some probability space, so omega space, Q is probability measure, and let's consider random vector on this space. So it's mapped from this to some vector space. I will assume that it has dimension n, but at least formally, it's not important. So we can take, say, Banach space or Hilbert space if you wish. Okay. In the case, if you have such picture, so in probability theory, they tell us that expected value of this x, we'll use this notation. It's simply integral of x over omega. And I will also will interpret this as a Q as some measurement device, and this is as a result of this measurement. So what is the problem? So I will play with these probability measures with these devices, and we'll try to measure vectors in this vector space. So say I want to take some vector, say small x from our vector space, and we'll ask, do we have some probability measure? So Q is some initial measure. It will be fixed at least during the lecture. So we trying to find another measure such that we expected value or result of measurement when you use this new device P is this small x. One condition that we will assume also that this new measure P, it's not very far from measure Q. It's we will see that there is density, some function rho, between these two measures, and then it will be a problem how to find such a rho that this integral will put here rho, so it should be equal to this small x. More or less obvious that you can find a lot of such rho, so it's not the problem at all. But we will try to find some more or less universal constructions that allow us to find this P more or less uniquely. What is this device? So if you assume that we have this space of measures, this is measure Q, and this measure P that we trying to find. So in geometry, usually, if you have such picture, so you should ask, so okay, you have this condition of your measure, and this P, you can play certainly with this P, but you can try to find P such that it will be the more closer to Q. So what we can say about, say, distance between two measures. So there is such interesting notion. It was really introduced by many people. So, and now it depends on country how we call this. So, because I am in Moscow, I will say that this formula was found by Kolmogorov just before Second War. It's the following construction. So we take something very similar to formula for entropy. So rho is our density, so rho logarithm rho dq. So we integrate this, we'll get some number. And what is this? What we know about this number, that this, first of all, it's non-negative. Is the first one. And the second, if this function equals 0, the measure p, then it simply means that p equal q almost everywhere. Or you can say that simply rho equal 1. So this is function. It can be served as some distance. It's not distance strictly speaking because it doesn't satisfy some triangle conditions. It depends really on order p and q. But it's not important for us. What is important for us that this requirement that this integral will be minimal really will give us the more closest to q measure p.
So actually, this I depends both on p and q.
Yeah, it's strictly speaking, I should write like this. But I said that q fixed it for us, so q will just say will be avoid to use the q. So there are a lot of names for this I. So I will use the more short. There is some term that is called relative entropy, but it's in relative entropy. In entropy, you should put minus here, and you have no such conditions for entropy really. So it's what we'll call not V, but what they call gain of information. So in some sense, if you pass from Q to P, you will gain some information. Okay, so I will add this condition and condition that I of P should be minimal. It's a very simple variation problem, and we know how to solve such. So what a condition? This one, and P should be probability measure. It means that really we assume that integral of rho should be equal 1. So we should add this to this if you think about density only. So this one condition, this another condition, and this is the third condition. So this is two constraints, and we should find minimal of all this. So how to do this? So we take functional that defined on these rows, and it's the following. So this is our I. So integral of rho logarithm rho dq.
The solution is p equals q.
Is p equals q? It will be not x. We choose this one.
Yeah.
And if you have your q, then you have some say, usually you norm this such that if you put here q, you will get 0 simply. And you're trying to find such p that it will measure this vector x.
So we fix X.
Yeah. So we take X and try to find this probability measure or density rho such that expectation will be this small x. Rho should give us probability, so integral of rho equal 1. And the second, that is this information again should be minimal. So,
Vale, can I ask you a question? It's Volodya Rubtsov.
Volodya, you can.
Tell me, please, can we put another type of constraint, say not only first moment, but second moment and so on?
Yeah, but not on this lecture, okay? No, it's
because you remember that it is sometimes very useful to impose energetic constraint. It means dispersion, second momentum constraint. It's like energy constraint.
Really, the only what I need. It can be vector, it can be anything that you want. The only should take values in vector space, because to get this integral, you should be able to add these quantities. So you can put any tensor instead of x. Say operator, anything. When you said second, say moment, I think you mean that I can put here x squared or something like this.
Absolutely, absolutely.
It's not a big problem. It simply means that this
element, it's just a question. It's not a problem. It's just a question.
And that will compute you what you want.
Okay.
Okay, but sorry, but I will be careful step by step, and we'll see what we can get really. Vector space itself, as I said, it's not important. It's finite dimension. It's also not important. The only what important here that this should be quantities that we should be able to integrate. So it's what they call in physics extensive quantities. So it's quantities that could be added. Okay. Anyway, so let's write this as a some variational problem. So this is our main guy that should be minimal, and the second guy, it's this one. It's this constraint, and plus, so lambda 0, it's some number. It's number. But this guy is take elements in V, so it should be something like this. Lambda integral of rho x dq minus small x. And lambda now, this is an element of dual space. So this is the classical Lagrange multipliers. And you should write, so let the F. Write this condition and try to find, I don't know, lambda 0, but main problem for us is this one. I don't think I should do this. It's very, very elementary stuff. So I simply give you answer how this will look like. How the answer will look like. First of all, this is our favorite rho. It will depend on lambda, on covector lambda, and it's invisible. It has this form. So this function on omega. So when I take value x at the point of omega with this random vector x naught, so this will be function on omega. Z lambda is function that depends on covectors, and it's a very nice function. And it has name, partition function. And finally, what is this small x? It's very easy to get from this formula. So if you just differentiate in lambda, you will get here under integral also x. And if you just divide it by z lambda and multiply by z lambda, you will get exactly this expression. So it means that if you have this capital X is random, so this X, I remind you, it's a vector varied function on omega. So using this function, you can construct this that we call, or they call, partition function. And using this partition function, you can write this formula for density. And the second relation between this covector lambda and our vector x is this one, or it's better to write like this, where h is what is a logarithm of that. So you have this. You can find this partition function by taking this integral in theory, certainly. Then you will find this function h, and you will get this equation that link our vector and this right-hand side function of covectors. Fine. Yeah, and name for this. All these names really I took from thermodynamics. Planck function. Oh, Planck energy. So really, thermodynamics can be all this picture in the thermodynamics can be get from this.
I don't understand. Z is a function.
Yeah.
Real value.
Function on this star.
It's a vector. Yes,
it's a vector. Yeah.
It's d lambda 1, d lambda 2.
Yeah. Really, I cheated. Yeah. You should put really this. Then it will be correct. Okay, so it's, I would say, trivial part, but it has very deep relations with geometry, and it's really based on this funny formula.
Are we assuming rho to be smooth?
What?
Is rho smooth assumed?
Rho?
Is it smooth function?
It's not assumed. Really, it should be a measurable function.
Oh, and then you can do differentiation in terms of it. You can do differentiations in terms
you
of
mean
it.
this differentiation? Yeah, I will assume that our function, our partition function is smooth lambda, at least in some domain of V star. And
okay.
And this is simply will say us that we can we'll able only some vectors, but not all.
Thanks.
Because yes, certainly when you write this integral, it's the question: do this exist? Is exponent, and it's can be, say, positive exponent, so it will be divergent. So it's really z lambda defined on some domain and blah blah blah. So I simply avoid all these technicalities. Yeah, certainly when I write the derivative, I assume that this function differentiated.
Sure.
Could be differentiated. Yeah. Okay. So now let's draw the following picture. I put horizontal. This will be V star. This will be V. So here it's a place where our lambdas live, and this is where our x's live. And here we have something like this: x equal dh d lambda. So first of all, I change a little annotations, and I will say that V star is not vector space, it's a manifold, and I will call this B in the sense that it's a base manifold. So V star cross, so B cross V, so so tangent space to V, it's V star, but cotangent space to V, to V star, it's our V. So really, this we can say that is cotangent is some say this one. It's cotangent space to our manifold V. So really, this is what I draw. This is a cotangent bundle cotangent space to this is manifold B, and what it is, it's a graph of differential of function h. So this is guy, let's call this LH. This is Lagrangian manifold, and what is we know that all Lagrangian manifolds in T star B that diffeomorphic to our base, they have this form for some function h. Okay, so this is the first sign that we working in area of informational geometry. So this is space of these lambdas. Lambdas is a label for our density or for our probability measure P lambda that corresponds to this function rho lambda. So we can think that is space of not all measures, but space only. This is very special measure. So let's call this extreme measure because it's give us a solution of our variational problem. It's the first one. And the second, there is this function I that we did not use yet. So let me. So let's compute what is this I. It will be the following. You can find easily. Really, if you remember this, that x is dh d lambda, I can put here h and think that this function in h, then it corresponds to Legendre transformation between two functions I and h. So this is our information gain, and this is Planck energy. It's also have some another name. It's called Gibbs free entropy. It's also in thermodynamics such kinds of expressions appears, and they also. But I like this is what energy, because it's give us some relation between two quantities that we like very much in physics, between information and energy, and they related by this is Legendre transformation. So if I will add here one more, so just simply one-dimensional space, so cross R, and here I will add, so put it on this I at each point computed, so I will get another, first I get another manifold, it will be really one jets of functions on B, and I will denote this for this label 1, and this will be Legendrian. So I will add here this expression. This. I will get Legendrian manifold in one jet space. So this is simply geometrical interpretation of all these calculations.
But you should say who live in this R dimension. Here we have lambdas.
So this is I of lambda.
I of lambda.
I just simply
Valentin Lychagin, but
yeah,
it looks that Gibbs free energy, not free entropy. It is standard name free energy
no.
in thermodynamics. Yes.
Volodya, I tested all these names, spent maybe 1 or 2 days. There are a lot of names for this, for different potentials. But
free energy.
Entropy.
I never met it. Okay.
Okay. No, I know that there are a lot of names that you can find in thermodynamics. So at least what is important for us that this is I will call this Planck energy. This is really Planck energy, and it's really the only name when they use it, Planck name. And this is for information. So I will try to avoid using entropy stuff like this. Right.
Because of your definition of information. Because normally it's because of your initial definition of information as integral of rho logarithm rho.
Yeah.
Because people usually call this entropy.
No.
Well, anyway, yeah, I don't want to discuss now.
To discuss terminology is the most interesting.
Yeah, the most interesting, I agree. Okay, but what we can learn from this picture? So, after a very short while, I will just show that all necessary probabilistic information about random vector we can get from this geometrical picture. So this is the basic. And to start our machinery, we simply need this Lagrangian or Legendrian manifold, and that's all. It's the first one, and the second one that here we get Lagrangian or Legendrian manifolds where lambda is a coordinate, so they can be projected on our base diffeomorphically. In general, if you just will apply this for situations in thermodynamics, you will see that, say, if you take water can be in 3 phases. It can be gas-like, it can be like liquid, or it can be crystal. So it's really 3 phases for one for water. So on this picture, it means that say for gas you have 1H, for liquid you have another H, for crystal you have the third H. So it means that in general you can get something like this. So this is your L, and here you have one H, here another H, and here the third one H. So we call this phases, and avoid. And simply we'll say that what we will need simple Lagrangian manifold in cotangent bundle, or Legendrian in jet space, in one jet space. And this is the only that we need. In one small name from thermodynamics, they have it's O. It's in thermodynamics they call equations of state. Really, say in this case, we defined our submanifold, our manifold, simply by n equations. So this is why they call equations, but they define state of our matter, and this is why they use this name. Really, this some physical laws like PV equal RT and stuff like this. So really, all these equations that you define define L, it's in physics they have some names, and it's not like in mathematics you simply write expression and don't care what it's really mean. Okay. So now I will play with this picture in two different ways. First, I will use what we know really about Lagrangian, Legendrian manifolds, about jets, and maybe we will need not only first order jets, maybe higher, when we will see very soon that we will need them. And it's one geometrical point that more or less I hope that is known for us. And the second is this probabilistic, hidden this probabilistic picture that we're trying to measure our random vector. So just follow to Volodya desire. I will.
A short question, if I may.
What?
A question, if I may. X is a derivation of H by lambda as a choice or as a consequence?
It's a result.
I see.
It's simply show you relation between this lambda with this covector and the vectors that you want to measure. So to measure this X, that you should find such a lambda given H, such that you will get this relation. In other way, you should solve this equation with respect to lambda and find necessary lambda for given X.
I see. So what you start with is H, yeah?
I not start with.
Sorry, what is the initial data in this picture?
Lagrangian manifold from geometrical point of view, from probabilistic random vector.
Okay, thank you.
Yeah. So now I just will go to first class at school and try to remember what we know from probability theory. First I will try to satisfy the Volodya desire. So let's try to find say moments, key moment of our vector X. But I should say what kind of measure I will use. I will use this extreme measure that corresponds to lambda. So this is a moment will depends on k. This is just natural number, and lambda that is covector. And what is the definition for this? It's not maybe very similar to what you can find in textbooks. So I will take degree of vector X. but the only degree that I can take, it's just a tensor degree. Or if you wish, I can say that I take here symmetric product of x on x on x. So sometimes you can write simply xk, but it's the same really, but it can be. I think it's more instructive than such form. And what it will be a result? So this is certainly it's a symmetric tensor. And so if you integrate symmetric tensor, you will get symmetric tensor. So it will be element of this space, symmetric power of our space V. And so it means that momentum is just symmetric tensor.
Why mk of lambda, not of x?
Lambda, it's rho lambda.
Yes, but our random vector is x, and we measure.
Yeah, x is just fixed forever, and lambda was that we can put it. So this only two variables that can be changed. Okay, so how to find this momentum? As I said, that we can simply differentiate this expression. So let's differentiate, say, once. So instead of x, I will write that x equal rho multiply on z. But that depends on lambda. It does depend on points on omega. So I will put here z. And here will be x multiply on also rho lambda dq. So if you differentiate this, you will get something like this. So if you take second derivative, you should differentiate this once more, but it's better to do not differentiate this, but take second derivative of this. When you will differentiate twice, you will get integral. Here you will get x squared. It doesn't matter what kind of symmetric product or tensor product, and x lambda x dq. And this is, as you know, it's once more rho, and here z. And so you see that this is a central second moment, and this is second derivative. So if you will differentiate many times, you will get the very fine formula. So mk is simply 1 divided by z, and here you should take case differential of z. It's case differential. It means case terms in Taylor formula. And really, this is the crucial relations for relations between geometry, between jets and probabilistic point of view. So when we're talking about some probability properties of this random vector, we will use this momentum, central momentum, and stuff like this. But from the geometrical point of view, you differentiate. You can write that z is exponent of h. You can write this as a some combination of derivatives of h. But what is important is that order will be equal k.
So actually, invariant is the whole family of m's, which is case jet of.
Yeah, that's it. So in jet geometry, we use it this once, and here we use it simply momentum. So And so it means that if you use second moment, it means geometrically that you working with second jets. If you use third moments, third order jets and stuff like this. Okay. Yeah, so certainly, yeah, I wrote only a simple momentum, but you can in easy way write formula for central momentum. Now about this guy, what is a case differential of function? Yes, certainly in general it's not correct notion, but we remember that our lambda is certainly element of our base, but its base it's vector space or affine space if you wish. And there you have standard connection, and all these differentials they take it with respect to this standard affine connection on this stuff. So it's so it's well-defined expression. Okay, but there is another another observation in probability theory. Say what we know. Say I will not say C2. It will be a central moment. It's M2 minus M1 square. But here square because it's a symmetric tensor of degree 2, and this is simply element of our space V. So this is square means V M1 multiplying on M1, where this is symmetric product here. So this element of S2V. And it also depends on point lambda. So this lambda, and this also lambda. So, and this is our picture. So let's repeat this. So this is our V star, this V, this is our manifold LH, and at each point lambda, we have this guy, element of this one. And as we know, V is you can identify with cotangent space to be in say in point lambda, for example, when you're talking about lambda. So
V plus V star is identified.
Yeah. So this is a fiber. It's simply T at point lambda T star V. So at each point lambda, you take symmetric symmetric element from T. So this is element of symmetric degree of T star. So it's in other words, it's symmetric differential forms of degree 2. So this is a module of symmetric differential two forms. So omega 2, it's omega 2, it's exterior, and this is symmetric forms. So
omega was a probability space. Let it be lambda.
Okay, lambda is for vector spaces. Okay, anyway, so I will use this notation. So sigma of some manifold, it means that we consider symmetric differential forms of this manifold. But as we saw, this LH is really diffeomorphic to our B. So you can say that it's formed either on Lagrangian manifold or on the base. I will prefer to talk about Lagrangian manifolds, because to compute this whole stuff, you see, we need really our H. It's not form of the B. So we can say that or simply by L. So the second central moment, it's give us differential form on our manifold, at least on regular parts. If you have something like this, then you have this form only on this part. It's not clear what happens in single point. Really, it will be okay. You will get really the smooth symmetric form on the manifold. Yes, but what we know from probability that this guy, it's usually positive. If it's really second central moment of some random function, then it's positive. So it's not really a number. So this, as we see, it's a symmetric tensor of degree 2. So we can say that, but in this case, we have this notion of positivity. So this condition, it's a requirement of probability. So central moment should be positive. When we just take our function h or our partition functions, use this formula, compute the C2, you have no idea what really happens. So you will get some tensor, but it's not clear, is it positive or non-negative? So what we should do, we should a little change our manifold. So I just now will write this L. And on this L, so it's our L, really there are domain where C2 positive. There is also some domain, some submanifold that C2 is degenerated, and there is some, the C2 is a negative. And so this has no sense from probabilistic point of view. So we should take our Lagrangian manifold and remove everything that concerns to negativity of C2. And finally, it's give us very nice geometrical properties that our equation of state is not simply Lagrangian manifold. It's Lagrangian manifold equipped with Riemann structure. Namely, C2 should be, if you remove this, you will get simply Riemannian manifold. The next guy is the question, the next step, it's, I think everybody will agree with me that why I should stop with 2. If I take, say, fourth central moment, it's also should be positive. If I take 6 moment, it should be also positive. So really, the question arises, so should I stop on the level of 2 or on the level of 2 jets, take only the C2, or I should continue and see, say, what happens in degree 4. It's
Well, as far as I understood, this is an intrinsic metric. It has nothing. It has nothing with any ambient structure of T star, initial T star. No. Nothing.
No, it's you see, if you have Lagrangian manifold in this situation, is T star of T star of yeah, then I can show it geometrically. It's really intrinsic, but not so. What you said. This is our V. This is our A. I take this point and take tangent plane to this. So tangent plane to this I can understand as a linear map from this tangent plane to this tangent plane. Yes. From say V star to V. And condition that is Lagrangian, it means that it should be a self-adjoint operator. or it means that this is tangent plane, I should consider as a, it corresponds to some quadratic form, because self-adjoint operator from this to this, it's simply some element.
My question was provocative, Valer, just to explain this. Thank you.
So in this case, it is really intrinsic. What?
Well, it depends on L.
Yeah, so yeah, certainly. It depends on L and depends on our situation, V and V star. If you take arbitrary V, then it's not true. Okay, so now what about next steps? It's the following. So I will take some expression, say, of degree 4, like x in degree 4 plus a1. I will omit in degree 3, so in degree 2, or say 4, 3, 3 it doesn't matter. It's on x, so it's. So I take this expression where a2, that's second degree tensor, a3, it's a third degree tensor, and a4, it's degree 4. So when you take this expression, this polynomial in x, so this element of S4V. And you can consider this a homogeneous polynomial of degree 4 on V star. So for polynomials, we have notion of positivity. So assume that we take this positive polynomial. Now, if it's positive or positive random tensor of in S4V, then if you take integral of this, it should be positive also, yeah? But if you take integral, this guy give you M4 plus A2 symmetric product on M2 plus A3, so M1 and plus A4. Should be also positive. Now the question, what are the conditions for our M's such that for any such positive polynomial, this polynomial will be positive? And Alec, can you, I will skip it. Yeah. Where is this expression? Slightly. Yeah. So really, this is a result. It's not difficult to prove, but not easy to prove. So this is a clear. It's a central moment. So what is claimed? That if you take any positive polynomial of degree 4 in this our vector x, take mean of this, you will get this expression, and this will be positive also only if C2, C4, and C3 satisfy this condition. C central.
Central moment?
Yeah.
Okay.
So this is central moments, but you see, this is second degree tensor, this is a fourth degree tensor, and this is third degree tensor. So altogether, it's element of 6th degree. And at least this we know from the previous, that the second central moment positive. So this is positive. This is, if you just move to this, it also will be positive. So this guy should be positive. So in particular, it means that C4 should be positive. But it's not enough to require that C4 positive. You should require namely this. So it's really conditions that involve second central moment, fourth, and third. So from probability theory, okay, more or less, it's more or less understandable what means C2. And this is two guys. There is very vague knowledge about them. It's so C3, they say that it's measure symmetry of our distribution, and C4, it's measure tails of our distribution. So it shows how far you can find valuable values for our distribution. Yeah, and so what it is really? It means that on this manifold L, but you see, it's not on L exactly, because it depends on second order or second jets of our H or Z. So really, it should not, we should take not L, we should take prolongation in second jets. So, but it's because we should take only regular parts, so they all diffeomorphic, so it doesn't matter how far you go. And this guy, it's positive in degree 4. It's give you this is a form, but like this one, this expression that we have, so 3C2 C4 minus 2 C3 square, it belongs to 6th degree symmetric differential forms on L. So it means that on this manifold L, we should require that C2 positive, but also this guy should be positive. So the 3C2 C4 minus 2 C3 square, it should be also positive, is the next condition. So it means that on our Lagrangian manifold, we have a Riemann structure, and this is 6th form. Honestly, I never met in my life such constructions when you fix manifold, Riemann manifold, and some 6th form on this manifold. Володя.
Yeah.
Oh.
Yeah.
So did you meet in your life the symmetric differential 6th form on Riemann manifolds?
Not immediately.
Okay, but yeah, but maybe you know a name for this. Anyway, this is some extra structure on Lagrangian manifolds that we should add to continue our study.
I'm a little bit lost with this inequality. I wanted to ask you, what's the algebraic origin of this inequality? 3C2 C4 minus 2 times C3.
What do you mean? How to get it, or what is this?
Yes, how to get it algebraic? What the algebraic meaning of? Is it some invariant? Is it some?
It's yeah, it's some kind of algebra, but what I try to explain is that if you have polynomials, you can write some condition for this A2 and 3 and 4, such that it will be positive polynomial. It's easy to write.
It's a condition of positivity.
It's condition of positivity. But after this, you will write this expression. It's now the tensor of degree 4. But it also requires that if this positive, then it should be also positive. And then you will get this condition for central moments.
But it is not discriminant, resultant, or something like this.
No.
No. So it is not some concomitant. No.
No.
No, you have two expressions, two polynomial expressions.
You
Maybe
mean this one?
no, I mean the positivity of first polynomial, the positivity of this condition M4, etc.
Yeah, condition positivity of this is some condition for this
Yes.
tensors.
And then
condition positivity of this guy.
It's only second one.
Yeah, you see, here you have more or less visible the polynomial of degree 4, but now it's not so, because it's not degree, it's not degree.
Yeah,
It's now tensors.
Yeah. Quite.
Okay. So this is what I want to show, that really sometimes probability theory help us to get some geometrical structure. So say Lagrangian manifold, not simply Lagrangian manifold, but Riemann Lagrangian manifold. And it's not all, it's also have some distinguished symmetric 6 form. It's also somehow have some list. So we simply stop it on the level of 4 jets, but we can continue and see what happens in high jets. Okay.
But then you should consider 6 order moments, and you will obtain something else, and so on. So
I really afraid to touch. I'm sorry, I'm lazy. It's conditions for polynomial of degree 6 is a positive. It's really 3 conditions. If you will 3 conditions, I really afraid to say. So it's just I really don't know. Do they have in algebra say some criteria when you simply polynomial, just polynomial in standard sense, not x, just simply number, not vector. So when say polynomial of degree 4 will be positive, when polynomial of degree 6 will be positive, and so on. It's not very difficult, at least it's not visible now, but I think I have some proof there how to get it. Okay, now let's continue. Let's see what we can do with this geometrical picture. So on one hand, we have this probabilistic. It's simply shift x plus something. It will kill. But because shift x plus something will kill. It can be killed every time. It's simply it's really you'll get the same condition. Simply it's better. It's much visible to work with such. Okay, now how to say that? Okay, so now I will talk about phase transitions. If you never read physical papers or physical books about phase transitions, I recommend you to read it. You'll get incredible pleasure to read all this. So geometrically, it's very visible and very natural. But if you just will talk about all the stuff without a geometrical picture, it will be not so good. So I will write our picture once more. So this is our E star B. This is L. So this is our V star. Oh, V, and this is our V star. And now I will take arbitrary Lagrangian manifold, something like this. So this is our L. So as I said, you can consider this is like one phase, it's another phase, and this is third phase. And existence of these guys is links to singularities of projection. So if you take, so let's P will be projection on base. So if you take projection of L on base, so there are singularities of this set of singularities of this projection. I will write single L, and at least it's area where lambda is not coordinates anymore. And if you take geometrical picture, or like say physical picture, if you write here, this is your B, let me write it's like two-dimensional. So this is our lambda. So if you take some path here, and we'll see what happens with your quantities when you will move along this path, then it's say, let's we simply think about say the second moment. So what will happen if you just will, or simply second moment, M2. So what will happen here? So as we know, it depends on the second jet of Z. So what will happen here? So what happens with derivatives, with the second derivatives when we will approach to this point? So this V is it's first derivative of say Z or H. And when we will go to this point, this is second derivative will tends to infinite. So it means that when you just will go along such path and will approach to this singular point, something happens. So your second moment will just blow up. So it's not regular behavior of your say this quantity, geometrical or physical or probabilistic, when you just will approach to this point. So if you remove all these singularities, you will get just our set of these phases. So this situation is well known from theory of Lagrangian manifolds. What really Arnold did when he investigated singularities of projections of Lagrangian manifolds on this manifold. So really, if you take this is singular and we'll take image of this singular, it's something that inside of our B. So this is what they call caustic. And when such situations appears not in our measurement picture, but say in quantum mechanics or in electromagnetic situation, in electromagnetic fields, then it's said where the more remarkable physical phenomena can be realized. It's like, okay. Anyway, so this is, I would say, a very well-known notion, and it means that if you just will continue to think about your system as a set of these phases, then it means that if you will approach to this, so somewhere you should, if you want to be in, say, finite domain for, say, for momentum, in some point you should jump from this branch to this or to that. It's not clear what kind of. So you have point here, you have something here, you have something here, and once more in thermodynamics they have this is very. So nobody will explain you why it is, but they will say that in this phase transitions, the intensive, so this is point, the image should be constant. So if you have this point, then I should jump to point where I have the same projection on V. So in physical language, it means that intensive quantities should be constant in phase transitions. This is situations that they call first order phase transition. From this picture, it's not clear should I jump to this or to that. And you remember that we have this C2, so you can easily check that if C2 here positive, then it will be negative here. When you just pass through this, you will simply change sign of C2. So really it means that you will never jump to this. I will give you a picture for van der Waals.
Yes.
Huh?
When you pass the catastrophe, and why?
Why not here? It's you can simply check it that if it's say the positive here, then it will be negative. It's convexity and okay.
So if one branch is admissible, then the next one is not admissible.
Yeah, it is not all branches admissible. Алик, покажи сам последний, там картинка есть. Сейчас, вот еще ниже, вот этот. Нет. Ну ладно. Ну вот, sorry.
Алик, а нельзя слайды выложить в чат? Потому что вот для людей, которые смотрят по Zoom, совершенно ничего не видно.
Это специально.
Я понимаю, да.
Ну, тогда вы Lychagina не увидите.
So so this is the case when you have real gas, say van der Waals gas, then intensive, or this is lambdas, it's temperature and pressure there, and this is causing. So this is a projection of this is singular that I wrote, and so you have situations that here you have say a gas, here say you have a liquid. And this is just not physical objects. Simply in this, when P and T will be in this area, you will never measure them with reasonable accuracy. And this is related to that C2 here positive, C2 here positive, but C2 here negative. So from a probabilistic point of view, this is not applicable.
It's in G1.
No, it's on the base. It's so this is our B.
Yes, it's the projection to.
So this is the singularities I projected on the B.
Yeah, and
so for gases, it's just temperature and pressure. And so this is the situation that here C2 positive, here C2 positive, but here C2 negative. And nobody knows what C2 there.
Always question, yes.
Yeah.
So if it's positive inside, then it is negative outside.
Yeah, it's when you just pass through this caustic, you will change the sign of C2. Okay, so this is very simple and very visible singularities, first jazz, but the more remarkable, it's so-called singularities of higher order, say second order singularity, third order singularity, and etc. Really, in physics, you can find a lot of opinions about existence or non-existence this type of phase transitions. And in reality, it's that this is singularity. They, in some sense, local. It's just defined by conditions that projection. So the differential of projection is just has non-trivial kernel. But the higher order phase transitions, they are non-local. So you cannot define them locally. And it's also some situations that we, at least I did not see in jet geometry before. So really, I will consider L together with all prolongations. I will take the only regular part. So it's I removed all this. So this will be L regular, and take prolongation of this. So I will get this in K jets. So in geometrical sense, I think that I am interested in higher derivatives of our Planck potential. Or from probabilistic point of view, I am interested not only in second moment, but in third moment, fourth moment, and etc. So what kind of singularities we can get? So this is, we just forget about Lagrangian manifold. You can simply say that you have integral manifold of Cartan distribution in K jets, and its manifold has a dimension n. And when you ask yourself what means singularity there, you can say, oh yeah, we should project it on base, and if it will have non-trivial kernel, it will be singularity. So something like this, simply in cages. So when I say that regular, I simply remove these options to have such type of singularities. So it seems that we have no singularities at all. Let's see. I will start with such a remark, or I think it's kindergarten problem, but anyway. So assume that we have covering, say degree m. It means that we have fibers with n points. And say so it's everything connected and blah blah. So this is simply one manifold projected on another manifold, and this covering of degree m. So it's really what happens if I take this one and take projection. So they will project it on base. It will be diffeomorphism on each pieces. So it's also will be just divided on some pieces where we can think that there are some part of this picture. Okay, now let's take function, smooth function on Y. I claim that there is a polynomial of degree m, something like z in degree m plus a1, z in degree m1 minus 1 plus etc. plus am, where ai's are functions, smooth functions on X, and our function f is a root of this polynomial. So any function on this total space Y is a solution of some polynomial of degree m with coefficients in X, smooth functions in X. Okay, I think Alec will put on the web this slides, and you can read it. This proof I gave this proof in this presentation, or try to do it yourself. Now, let's assume that we have this picture, but y, it's just piece of this RK regular, and x, it's a part of our base B, so this projections PK, and we took some piece of this and this such that it will be covering. So now let's so this is in kjets. So here you have the standard coordinates. Okay, say lambda, u sigma. So lambda, this is coordinate on B. U, this is coordinate, it's just function, and this is also, it's just standard coordinates in jets. So I take the highest, this u sigma. So length of sigma is a k, and take this as u sigma is a function here, and so here also. I take this and apply this as a result. Yeah. No, no, it's I didn't claim that it will be everything, every time. So I think we say that if such situation can be realized here, then I just will get some kind of singularity. And this is what I said. It's not anymore local. It's a global. So because the question is how to find this y in this, and it should be not something local. It should be some manifolds there. Okay. So what we know that there is this polynomial of degree n, such that u sigma is the root of this polynomial, and coefficients just these coefficients, they just coefficients in x. So not in x, I'm sorry, in our case it's coefficients in lambda. Now how to get prolongation of, say, this manifold? I should simplify, I should differentiate this to find u sigma plus 1, right? So let's take derivative, say lambda, it's lambda 1, lambda n, and let's take derivative of this Pm u sigma. So I will assume that this coordinates z is just put it for this argument. So what it will be? It will be d Pm dz on u sigma plus 1I plus, so simply the differential of this d lambda I equals 0. So this equation for this one so to find this u sigma plus I, so next u, it's very easy from this, right? But only if this guy different from 0, and this guy we computed on u sigma, on the root of this our polynomial. So it means that in the case your derivative and polynomial have common root, we're not able to find this. Then this is u sigma plus 1 will be just infinite. So it means that if you take discriminant of this is polynomial p sigma, then if you just sit outside of the discriminant set, Pm, yes, Pm. So if you just outside of this is when discriminant equals 0, then there we can find this is u sigma plus 1. But if you just at the point of this, then this guy will goes to infinite when we just approach to this point on this set. And it's exactly the situation with this projection that we considered, where second derivative tends to infinite. So what it means that if I have such situation, then I should consider all possible discriminant sets. And because what means all possible? Because we have a lot of this U sigma, right? So for each U sigma, we should find this is discriminant set. And outside of this discriminant set, everything okay. So it means that I can prolong this, and we'll get this k plus 1 manifold in gk plus 1, but it happens only outside of these points. These points are not prolongable. Here, after prolongation, it just will go to infinite. So this is exactly the situation that we saw on the first order phase transitions. There also, when we just approach to the singular point of projections, we saw that second derivatives will just also tends to infinite. And now we will see that in all this manifold, we have prolongible and non-prolongible points. And they depends on this set. And this, because it concerns to high order jets, so this is why the name that this sets corresponds to higher order phase transitions. So it's not visible, yeah? You uploaded. Okay. So Алик, подними там, где там красненькое еще должно быть. Вот это, да. So this is picture that contains phase transitions of the second order and the first order for van der Waals gas. So this is the red line. It corresponds to first order phase transitions. Remember, I draw this triangle here. And yeah, this is a picture on the page number 9. So the red line is the first order phase transitions. Now we have really, in our case, is two variables. So and this is second order derivative. So we have 3 second order derivatives. So we should try to find discriminant sets for 3 polynomials. And so the blue one is the one. This is the second one. And the third one, I forgot. Maybe only 2 sigmas give us this is curves. So this is the phase transitions of the second order. What they mean physically, say for this case, it means that if you take some quantity that contains physical quantity that has infinite has second derivative, then approaches to this point, and you will get this phenomenon. So this guys will go to infinite. So it means that the value of this physical quantity will grow. Physically, it's nonsense, but mathematically, you will approaching this, you will get some infinite values in some physical quantities. As far as I remember, it's if you take speed of sound in van der Waals, it has second derivative in the descriptions. Only this is heat capacities. They also use second derivatives in computation. So it means that when you approach to this or to these points, you will get this phenomena for yeah, certainly it's very difficult to get infinite velocity, but anyway, in some domain here, you will get it. So, and in physics, this is the vertex of this red line is so-called critical temperature for gas. And if you see that there are some second order phase transitions in neighborhood of this critical value of temperature, and there are something that's very far from critical values. So it means that physically it's very difficult to construct experiment and to find these phase transitions if you don't know where this curve or this curve where they're located. Okay. What time? 9. Я могу сказать, что...
Ну, если у тебя еще есть логические.
Там много чего. Лучше, да.
Okay, thanks a lot. It was very interesting. Questions, remarks? Не слышно?
Да.
No question, no remark.
Ну, столько квестионов было по ходу, вообще-то. Я правда, не буду
Well,
упираться.
please speak English.
Sorry.
If you can.
Well, you know, every day it's much more, it becomes more and more difficult.
What
do you mean?
I mean that just to change 3 languages in one head, it's a kind of trichotomy.
We have no 3 languages here. We have just 2.
No, in my head it's 3. What to do?
Okay, choose one.
Okay.
So,
I'm speaking in the same time trying to speak 3 languages.
It's a remark. Yeah. Okay. Yeah.
It was a remark, or you have a question?
Just a complaint.
A complaint. Okay. Well, we are with you.
No, the remark was the following. I would like to have more, how to say, more reasons just to call information what people call entropy with minus. Just only one difference with your quantity, minus in front of this integral, and people call it entropy.
No.
Usually, I'm sorry, Valentin Vasilyevich, but it is.
Well,
Alec, can I share screen, please?
You mean this expression for entropy, where you see a cube?
No, not this.
Which one?
I mean, it is also expression for entropy, but I want to show you another expression for entropy. Not
Okay.
another reason. I mean, another argument. It is
Okay.
just argument is the following, that entropy, Hipps entropy, it is integral minus integral of p log, integral rho log rho, like you wrote. But
yeah, but integral has.
it's a question of name. Okay, I don't want.
No. Waller's definition was different. Because in your definition, there is no Q.
Yes, Q is you integrate by Q.
What is a Q then? In my case, it is some quasi distance between 2 measures. And what is the entropy? Okay, it's not my term.
Yes, we can discuss it. For me, it's a question of name. Just that's all.
Not only, but in coding theory, this information has very explicit description in terms of what we mean by information. There are different understanding what means information. So this is simply name here, but there are also some available constructions behind this.
Okay.
But,
Can I share the screen, please?
Он хочет, чтобы на его экран.
It's not for everybody, but
Yes,
for
yes,
those
you can do it.
I'm doing. And look the definition, just definition of Hipps entropy.
Валя,
и что? Gibbs has nothing to do with entropy at all. It's goes to Boltzmann and after Shannon and stuff like this. It's Volodya,
That's why
I'm very skeptical about entropy at all. It's not a well-defined notion in thermodynamics.
well, this is a personal, of course. I understand.
Yeah, certainly. I said that I didn't
Yes,
say
of
that
course.
you
But
are.
actually, we are arguing about
Just-
words, not about oceans. So
We speak about name. Yes, that's the point. Here it is.
No. It's not about name. I simply wanted to show that this is notion. It's very important when you you want to find another measure, and when you use this quasi distance as a way to compare one measure with another measure.
Please explain me what's the difference between this formula and your definition. The
Which
formula
one?
number one. Number one. Just the first formula. It's a classical statistical mechanical entropy.
Yeah, there is here dx. What is a dx in this formula?
What is your DQ?
Huh?
What is your DQ?
No. If it's Lychagin measure dx, then this formula has no sense at all.
So just okay, it's a volume measure.
No, it's a volume. Is yeah, I agree, but it's not probability measure dx here. It's just a big measure, and you write this formula, and it's just nonsense, really. So if I have this probabilistic space, where x will take.
Well, it's philosophical question. Okay,
No.
Yes,
Yes. It's your formula number one, where there is some expression. It's started with a dx, as if I understood x is just element of n, and dx is just simply standard Lychagin measure there.
it's
well, but it's
your formula is a little.
то же самое, что вот это.
Yeah.
Просто это дискретно, это для непрерывного распределения. Нет, конечно.
This is also rho. It's also probabilistic measure. I mean probabilistic.
No. Rho it's not probabilistic. Rho dx. This is a probability measure, right?
It's a probability density.
For
it is just a classical physical system. If you want to associate with this some sigma algebra and so on, probably we can establish correspondence between this formula and your formula.
Yeah, no.
Рубцов, ты чем критиковать, ты бы лучше статью написал, прислал мне ее.
Yeah. It is not a critic. I just want to understand what is critic. It's not a critic at all. I just want to understand. And I think that it is more or less the same.
No. Well, okay. Just because you like names. So
No, I don't like name. I like formulas.
Yeah.
I like the formulas. Name, for me, it is not important.
Please give me what you can give me just a couple of minutes. I will just explain you. Really, the relations between finite case where they use this formula and infinite case, it discusses it not for hours, for tens years, maybe more really. And the first sign when there is some formula for continuous measures, not like this, but what you wanted to show me.
Ты можешь написать аналог дискретный для вот этой формулы?
Для моей?
Да. Ну, чтобы было видно, чтобы разница была видна.
Oh, because they're nice. So the problem that for discrete case, if you will try to take this formula and write for continuous distributions, you will get nonsense. That will just all integrals will be just not converted, and there is no sense. And first time it was, at least from my point of view, first time it is in the paper of three unknown mathematicians, Gelfand, Kolmogorov, and Nikolov. They published this in Yeglov. It was, they published a paper where they explained how to write entropy or entropy-like objects in case of continuous distributions. So
yes, yes, this is I agree
now
with
now it is called Kullback blah blah divergence. But it's more or less common that if something written here, it will be not known on the West. It's but it's the first attempt, and it's not. It was published in in Doklady Academia Nauk, and it was considered, at least Kolmogorov in his memoirs here wrote about this, and he put it on the first place that they found this formula. Really, Gnedenko, before just Second War, he gave some talk about how to write this formula. So it's not very easy. It's not simply play with one integral and another integral. There is very deep mathematical and physicals behind all this. So it's not entropy at all. I am sorry.
You know, I knew this formula for continuous quantities from the paper of Yeglov and Gelfand student Pinsker, who wrote a book about it.
Pinsker, they wrote it in 60s, or it was
not in 60s, in 50s, and
no.
and
Okay.
he called it entropy. What to do?
Okay, Pinsker is the student of Kolmogorov, so it was after this it was just simply it's not discovery of this formula, it's simply development of this formula.
Well, Volodya, anything else?
No.
So any more questions, remarks? Okay, thanks a lot. It was a very interesting talk, and I would like to say that we have again a change of our program because our design speaker is still ill, so the next talk will be by Rafael Vitola, and we hope that in 2 weeks we shall have the talk by Kushner. So have a good week. Goodbye. Thanks for participation.